Good morning, dear students. So today I am going to start a series of lectures on a very important topic in mathematics, especially for postgraduate students and the students who are going to appear in UGC NET entrance examinations in the coming times. The topic is metric space. So we will have a lecture series on this topic, that is metric space. So first of all, what a metric space is? A metric space is a non-empty set X along with a metric D. Metric D here, metric D means a function D. D is actually a function whose domain is the Cartesian product of X with X. So D is actually a function from X cross X to R plus. R plus I have written because it is the set of positive real numbers. We will not consider negative real numbers. That means R plus here means from 0 to infinity. Closed 0 to open infinity. So that means 0 is also included. So D is a function. Now it is not a simple function, it is a function that will satisfy some properties, some axioms. So what these properties are, what these axioms are, these are, I'll denote these by M1, M2, M3 because it is metric, so why I have taken this M. What is M1? M1 is the symmetry. M1 is the symmetry property. Symmetry property means D of xy is equal to D of yx for every 2 points x and y of this set X. Whatever the values of x and y, you take it from this set X, so x and y, then symmetry property will state that D of xy is the same as D of yx for every 2 points x and y belonging to the set X. The second property, M2, is the positivity. So what is the positivity property now? It states that D of xy is always greater than or equal to 0, whatever the values of x and y from the set X. So for every 2 points x and y from the set X, D of xy will be greater than or equal to 0. The third property is equality. The third property is equality property. Equality. What the equality property states here, that D of xy is equal to 0 if and only if x is equal to y. So that means if dxy is equal to 0, then x is equal to y, and if x is equal to y, then dxy is also equal to 0. So it is vice versa. So this is the third property for D being a metric. And now the fourth property, M4. The fourth property of the metric space states that the name of the property is triangular inequality. Triangular inequality. It is a property, triangular inequality. Triangular inequality is the same as that you have studied in your 8th class standard, that the sum of two sides of a triangle is always greater than the third one. Here it is almost the same, that is D of xy is less than or equal to D of xz plus D of zy for every 3 points x, y and z belonging to the set X. So if these four properties are satisfied, we will say that D is a metric, and the non-empty set X along with metric D will be called a metric space. Now the question is, why have we denoted this particular function, that is metric, by D? The reason being, whatever these four properties are satisfied by this function D are basically the properties of distance function. So if in Euclidean space or in two-dimensional or three-dimensional space, you can check that if 2 points of x and 2 points are there, x and y, then distance between x and y is same as the distance between y and x. Then distance between every 2 points is always greater than or equal to 0. Distance can never be negative. The third one is that the distance between 2 points is 0 if and only if the 2 points coincide. That is the third property. And the fourth property, as I already have stated, that it is a triangular inequality which you have studied in your 8th class standard. That means the sum of two sides, that is distance between x and z, the distance between z and y, and this is distance between x and y. So if x, y and z denote the vertices of a triangle, then this is one side, this is the length of the other side, and this is the length of the third side. So the sum of the lengths of the two sides of a triangle is always greater than or equal to the third side. That is the triangular inequality. So why this function metric, normally we denote it by d because it satisfies the properties of distance function. Now, if we go into the history, I would like to tell you that this metric term was first time used in the year 1906 by Maurice Fréchet, and this was especially used for functional spaces, especially discussed by Cantor, Volterra, Arzela, Hadamard and Ascoli, and several other mathematicians too. After some 8 years in 1914, the metric space and the term metric was used by Felix Hausdorff, and he used it in topological spaces. After 8 years again, in 1922, Kazimierz Kuratowski used it in very detail in several fields of mathematics. So after the definition of a metric, now we look at some examples of metric and metric spaces. Now, as I have discussed you earlier, metric is basically the distance function. So what the first example should be? The first example should be distance in the real line. So if you take your x to be r, then d is a function from r cross r to the set of positive real numbers including 0, that means 0 to infinity. And now we define this function as d of x and y as the distance y minus x mod, that means the distance between the points y and x. And as I have discussed earlier, that distance always show the symmetry property. Distance between 2 points y and x is the same as distance between x and y. That means this can also be written as mod of x minus y, which means d of xy. So d of yx. So d of xy is same as d of yx. The first property is very much clear. For the second property was positivity, and you know that is the modulus function, the absolute value, and absolute value of any number is always greater than or equal to 0. That means d of xy is always greater than or equal to 0. The third thing, that is the equality. We know that mod of y minus x is 0 if and only if y minus x itself is 0, if and only if y is equal to x, that means x is equal to y. So d of xy is equal to 0 if and only if x is equal to y, which is the third property of this metric function. The fourth one is triangular inequality, and that we know is true from our middle class standard 8th class knowledge. We know that triangular inequality property always holds for distances in the two-dimensional space. Now we move on to the other examples. The next example from R, we can move on to the next example to the Euclidean space of degree n, that means Rn. So if we move on to the Rn, Simply, first you take, if what happens if we take r square. In r square, the distance between 2 points x and y is x minus y distance. Normally we used to denote it by x1 minus x2 square plus y1 minus y2 square, where the point x is x1 y1 and the point y is x2 y2. So this is, we know from our basic knowledge of geometry, that the distance between 2 points is this. You can write it also as sigma xi minus yi square under root, where I vary from 1 to 2. You can write it like this. This is for 2 dimension. We can further write it as sigma I vary from 1 to 2 xi minus yi square and raised to the power 1 by 2. This is the distance function in 2-dimensional space. On the plane, 2-dimensional plane, we can define distance like this. If we move on to the 3-dimensional geometry, that means the solid geometry, what will happen? We will have here the distance xi minus yi square. I vary from 1 to 3 now, because now we will have 3 coordinates and the power will be 1 by 2 again. So what it means, if we move on to the n dimension, the distance will become, our dxy will become sigma I vary from 1 to n xi minus yi square and raised to the power 1 by 2. So it is a metric. Why? Because it is again distance in n-dimensional Euclidean space, and for distance we have seen that the metric D satisfies all the 4 properties as stated above, like symmetry, positivity, equality and the triangular inequality. Now we move on to another very important example. In practical, if we look into the surface of our earth, on the surface of our earth, if we take the set x as all the points on the surface of the earth, then what the metric D will be? The metric D will be the distance between any 2 points on the surface of earth, and the distance is considered along the great circle. Then this will again be a metric, and the surface of the earth as a set of points will be the metric space. Another important example of metric spaces is discrete metric space. So what is the discrete metric space now? Discrete metric space, let X be any non-empty set. Then we define D from x cross x to r plus as D of xy is equal to 0 if x is equal to y, and 1 if x is not equal to y. That means distance between any 2 distinct points is 1, and if the point coincide, then the distance between the 2 points will become equal to 0, and this function, this D, also satisfies the 4 properties. The reason being, look into the first property, that is the symmetry, M1 property we talk about. Then D of xy, look at, suppose x and y be any 2 points. Let x1, y be any 2 points on x. Then 2 things may happen. Either x is equal to y or x is not equal to y. If x is equal to y, then what will be D of xy by the definition? When x is equal to y, it will become equal to 0. And what will be D of yx? Again, since x is equal to y is also equal to x, and y is equal to x means D of yx is also equal to 0. And this implies that D of xy is equal to D of yx. Now, if x is not equal to y, then D of xy will be equal to, x is not equal to y, so D of xy will become equal to 1. And what will be D of yx? Since x is not equal to y, so y will not also be equal to x also, and y not equal to x again implies that d of yx is equal to 1, and again it implies that d of xy is equal to d of yx. So the first property is clearly satisfied whether x is equal to y or x is not equal to y. Now we move on to the second property, M2. The second property, M2, that means the positivity. So again, there are two cases, either x is equal to y or x is not equal to y. If x is equal to y, then d of xy by our definition will become equal to 0. And if x is not equal to y, by our definition d of xy will become equal to 1. Whatever the case, either the value is 0 or it is 1, we can deduce that d of xy is greater than or equal to 0. If it is 0, then also it is greater than or equal to 0. If it is 1, then also it is greater than or equal to 0. That means the positivity property is also satisfied. Now we move on to the third property. D of xy is equal to 0 if and only if x is equal to y is clearly given in the definition itself. In the definition you can see dxy is equal to 0 if x is equal to y, and if x is equal to y, then dxy is equal to 0. So third property is directly following from the definition. Now move on to the fourth property. Fourth property, M4. Again, we are having 3 points, x, y and z, and we will look at all the possible cases. If x is equal to y is equal to z, if all the three are equal, then d of xy is equal to 0 by definition, and d of xz plus d of yz will again be 0 plus 0 is equal to 0. So if we write 0 is less than or equal to 0, it's not wrong, it's correct. Second case, suppose now I am changing the values and we look whether it is less than or equal to again and again or not. If x is not equal to y, but y is equal to z, x is not equal to y means this is equal to 1. X is not equal to z, this is 1. Y is not equal to z, so this is equal to 0. So this side is 1, this side is also 1, so we can say this is again less than or equal to, the 1 is less than or equal to 1, that means the property is satisfied. Now move on to another case. Now the case, here we have taken that x and y are not same but z is same. If we take y and z are not same but x is same, it will be the similar case. Again, if we take that x is not equal to z but equal to y, it will be again same. That means if any two of them are equal, the third one is not, then the property will be almost same. Now the only case remains is that if all three are different, x is not equal to y, is not equal to z, and even x is not equal to z, then d of xy will be 1, d of xz will be 1, d of yz will also be 1. So left hand side is 1 and right hand side is 2. So 1 is less than or equal to 2 is again right. So the fourth property is once again satisfied. So that means this d defined by dxy is equal to 0 if x is equal to y, and 1 if x is not equal to y is a metric since all the four properties are satisfied. So this metric is called discrete metric, and the space along with this metric will be called discrete metric space. Now we move on to another very important example as well as solution of a question. Now the question arises in our mind, on a set X, how many metrics can be defined? At least one metric we know that we can define, that is a discrete metric space. At least this one is always possible. Secondly, if there are more than one points, then the distance metric is also there always. Now the question is, how many metrics will be there on a set? Suppose X is a metric space with the metric D. X is the set, non-empty set, and D is a metric defined on it. So XD is a metric space. Then we again define a function D dash from X cross X to the set of positive real numbers including 0. we will define it as d dash of xy is d of xy divided by 1 plus dxy. Very interestingly, we will see that d dash is also a metric and it is deduced from d. So first we will check whether it is a metric or not, because all the 4 properties must be satisfied. The first 3 properties are, I think, very easy. Symmetry property. Here you will take d of xy is equal to d of yx because d is a metric. D of xy is equal to d of yx because d is a metric, and it will turn out to be d dash yx, and d dash xy will become equal to d dash yx. The second property is that positivity. If dxy is positive, then this is positive. Numerator is positive, denominator is positive, so the fraction is again positive, so that means d dash xy is greater than or equal to 0. The second property is also very much clear. The third one, that dxy is equal to 0 if and only if x is equal to y. Suppose x is equal to y. Since x is equal to y, this d of xy will become 0 as d is a metric given. So 0 upon 1 will be 0, so d dash xy will be again 0. Conversely, if d dash xy is 0, so this is 0, 0 is equal to this, cross multiplying, you will get dxy is equal to 0, but dxy is equal to 0 will imply x is equal to y because d is a metric given. So first 3 properties are obvious. The main is the 4th property on which we will have some concentration. How to prove the 4th property, that means M4. Now d dash xz plus d dash zy. I want to prove that this is greater than or equal to d dash xy. That is what I wanted to prove. So I will start from this side and I will show that this is greater than or equal to d dash xy. So I am starting from this side. What is the value of d dash xz? By the definition is d of xz divided by 1 plus d of xz plus d dash of zy is d of zy divided by 1 plus d of zy. I think it is clear to you now. So this is a fraction and numerator as well as denominator is positive, so it is a positive fraction. In a positive fraction, if I increase the denominator, what will happen? The total quantity, the total fraction will decrease. So what I am going to do, I am going to add to the denominator of this quantity, that is dxz divided by 1 plus dxz. This was with us, and I am going to add d of zy here. And d of zy is positive because d is already a metric, so this quantity is positive. I have added some positive quantity to the denominator of this quantity, so that quantity will be greater than or equal to this quantity now. Plus, similarly, I am going to add here in the denominator 1 plus dzy, and I am going to add d of xz. I am going to add here d of xz. Now, this is equal to, if I take the LCM, now both the denominators are same, d of xz plus d of zy. In the numerator you will get d of xz plus d of zy. Take this term, the numerator, into the denominator of the denominator. So what you are going to get now, 1 upon 1 plus 1 upon d of xz plus d of zy. This term you will get now. Now look, here I am going to do some rough work. D of xz plus d of zy is greater than or equal to d of xy. Is it right? Yes, it is right because d is already a metric. Taking, and both are the positive quantities. So what will happen if I take the reciprocal on both sides? It will become 1 upon d of xz plus d of zy is less than or equal to 1 upon d of xy. Just I have taken reciprocal. And now add 1 both sides. Add 1 here, add 1 here. And take LCM on the right hand side. So you will get, I am writing here only, this is 1 plus d of xy. Once again, take reciprocal on both sides as both the quantities are positive again. So what will happen if you take the reciprocal? The sign of inequality will once again change. So you will get 1 upon 1 plus 1 upon d of xz plus d of zy is going to be greater than or equal to d of xy over 1 plus d of xy, and this result I am going to use it here now. You are getting this quantity here, so it will become greater than or equal to d of xy over 1 plus d of xy. But what it is? By our definition, it is equal to d dash xy. So that means your d dash xz plus d dash zy comes out to be greater than or equal to d dash xy, which means the fourth property of the metric. That means d dash is also a metric. So that means from a metric d we can induce another metric d dash. Now from d dash, by the same way, defining d double dash is equal to d dash upon 1 plus d dash, we can have another metric. Then defining d triple dash is equal to d double dash upon 1 plus 2 times d double dash, we can have another metric. And continuing like this, we can have infinitely many metrics on the same set. So the question, how many metrics are there on a non-empty set? The answer to the question is there are infinitely many metrics on any non-empty sets with at least 2 points. Now, the next I am going to give the definition of a pseudo metric space. What is pseudo metric space? In pseudo metric space, the things are almost same, leaving the one property. That means the third property, we were saying that in the property of equality, we were saying that d of xy is 0 implies and re-implies x is equal to y. This was the third property in the definition of metric space. If I change this property into the property d of xx is equal to 0 for every x in x, if I drop the third property of equality and I change this property to this from this property, the definition we will obtain will be the definition of a pseudo metric space. That means what is happening now, look carefully. Earlier in the metric space, we were given that if dxy is equal to 0, then x is equal to y. If x is equal to y, then dxy is equal to 0. Now what is going to happen? If x is equal to y, no problem. d of xy will be 0 again. But if d of xy is 0, it need not now imply that x is equal to y. Now, distance between two distinct points can also be 0 in pseudo metric space. That is the difference between the metric space and the pseudo metric space. And where it is applicable? It is basically applicable where we are considering the equivalence classes. In equivalence classes, if I take 2 points from the same class, then if we define the function as the distance between 2 points is 0 if they are from the same class, and the distance is 1 if they belong to different classes, then the first, second and the fourth properties are obvious of the metric space. Now look at the third property. If 2 points are same, no problem, they are in the same equivalence class, so the distance will be 0. Now, if you take 2 points from the same class, 2 distinct points from the same class, since both the points are distinct but they belong to the same equivalent class, the distance will become equal to 0. So dxy will become equal to 0 even when x is not equal to y. Actually, x and y now are belonging to same equivalent class, and the metric considered will not be a metric, actually it will be a pseudo metric. There are several other examples. Suppose you take a set of all continuous functions from closed interval 0, 1 to the set of positive real numbers. So let f be a function from, we'll take this from 0 to infinity to r, and we consider it to be a continuous function. We are taking, you can change it to even ab. Not if you don't want to take 0 infinity, then you take the closed interval ab. And on the right side you take r plus. Then consider all such functions, the set of all such functions f. So let it be your x now. Let it be your x now. Then several examples of metric spaces and several examples of different metrics can also be obtained. For example, if we take d of f and g. F and g I have written because now our set x is containing functions. So f and g are the functions now. And I define d of fg as supremum of mod of fx minus gx, where x belongs to the domain function, that is the closed interval ab. Now this will again be a metric. You can prove, take it as an exercise, you can prove it that it is a metric. Another example you can have d of fg here. D of fg here. Here again I am considering the same x. And you take integral from a to b mod of fx minus gx dx. Then this d will again be a metric. It is another exercise for you. You can check it, you can go through it, then it will be a metric. And x will become, along with the metric d, will become a metric space. Even if you take square of that and then take power 1 by 2, then again it will be a metric, d will be a metric, and x along with d will become a metric space. So there are many examples on metric spaces with different sets x. So try to find different examples, different sets and different metrics on them, and try to prove that they are metrics. So I am going to stop the lecture here. In the next lecture we will discuss more and more about the metric space and several theorems related to metric spaces. I think you like this video. You have some knowledge about metric spaces from this. So it's my request, if you like it, then kindly show your like in the YouTube, share it with your friends, with the postgraduate and graduate students of mathematics in your area, in your friend circle, and subscribe the channel for the coming videos on this metric space and several other topics that are useful for your several entrance examinations as well as for UGC NET examinations. Once again, thank you.